Hello guys, how are you today? So today I'll be explaining the physics AMS of term 2 week 3. I'll start with the first question. A 0.8 kilowatt washing machine works on 220 mains volt supply. So we have the power over here. And then over here we have the voltage. The current flowing through it during normal functioning is 3.6 amperes. So directly without solving, they gave us the current. And they told us, which of the following fuses is most suitable to use for protection? So, which fuse is most suitable to use for protection? And if we look at the answers, what will we see as options? We will see we have 10 ampere fuse, 2 ampere fuse, 1 ampere fuse, 4 ampere fuse, and 3.6 ampere fuse. Okay, so 10 ampere for sure is not gonna work because we're dealing with a 3.6 ampere current. Then 20 ampere for sure is way too high. 1 ampere is way too low. Now we are left with two options, which are 4 ampere and 3.6 ampere. 3.6 ampere is the same as this one over here, but what is happening is that, okay, if a current slightly greater than 3.6 will cross the fuse, it will not do damage to this machine. Because in reality, its current is not actually 3.6. If you calculate its current, it's going to be the kilowatts. So it's going to be 0.8 times 10 to the power of 3 over 220 volts. You're going to get it to be 3.63636. So it's a never-ending decimal. Okay? So if you use 3.6 ampere, which is lower than it, it's definitely not going to work. That's why you always have to choose a value that is higher, the nearest value. So in this case, it's gonna be 4 ampere fuse. But if you use the 3.6 ampere fuse, a slight fluctuation, so it's 3.6 ampere, a slight fluctuation, meaning a 3.63636, okay, which happens, okay, it could happen, okay, it will cause the fuse to blow. We know this because it will cause the fuse to blow or it will cut out the circuit. And then the device will not function. So you will just end up having a device that does not function. Whereas if you use a 4 ampere fuse, it reaches this value, which is 3.63636, and the fuse will not blow unnecessarily. So very simply, this is why the first option is 4. We move on to question number 2. A plane wave strikes a straight reflector as shown below. So you will draw the straight line, and because it is a reflector, it is a surface, okay, we will have to draw the normal. So when we draw the normal, which is like this, we will now have to draw the reflected ray. And remember, the angle of the incident ray and the reflected ray always have to be equal. So this angle over here is equal to this angle over here. Okay, so remember, you will deal with it like a light wave, just like any light wave. It will undergo the rules of reflection, okay? And you will be resultant with a wave that is reflected. It will have the same angle of reflection, and it's gonna be just the same but reflected. So in this case, we drew it and it was going upwards. So it was gonna go like this, upwards. So which one has the ray going upwards? It's this one. So this is our answer. We move on to question number 3. A ripple tank is set up to hold 2 regions of water, deep and shallow water. An oscillator is used at one end of the ripple tank to create a water wave as shown below. Now what we need to know, what happens is that when we're going from deep water to shallow water, we have refraction occurring. And what happens during refraction is that the speed of the waves will decrease. So if in deep water speed is higher, so we're going to say that in deep water the speed is higher. In shallow water the speed is gonna decrease. And because the speed decreases, you will see something which is refraction. Okay, so drag and drop the correct terms to compare the properties of water wave in deep water to the properties of the water in the shallow water. So when we are moving from deep to shallow, we are undergoing refraction. Okay, in the deep side, what do we have? We have that the frequency, it is equal to what? The frequency in the shallow. So the frequency never changes. It always stays the same whether it's deep or shallow. Now, the wavelength in the deep, it is greater than the wavelength in the shallow water. And now finally, the speed of the wave in the deep is greater than the speed of the deep in the shallow. So the frequency, as we know, it is the same, okay? The wavelength, it is greater in the deeper water than in the shallow water, and the speed is greater in the deeper water than in the shallow water. So keep this in mind, all right? So when it moves from deeper to shallow water, it will undergo refraction. Okay, the frequency will stay the same, but the wavelength will decrease and the speed will decrease. We move on to question number 4. The diagram shows a ripple tank as seen from above. An oscillator is generating straight water waves toward a gap. How will the water waves behave after they pass the gap? Look what's going to happen. We have the water waves, they are straight line, and then we have a gap. When they pass through a gap, they will diffract. And when they will diffract like this. And what you need to know is that the smaller the gap, the more curved the diffraction will happen. Okay, so if we had a bigger gap, let's say these are the waves, but we had a bigger gap like this, they would turn out like this. So they wouldn't be really diffracted, they would be partially diffracted. Okay? And then, if we have two gaps, let's say we had a gap over here and a gap over here, we would have something called interference. So we'd have these waves coming like this, and then these waves coming like this. And interference is where the two waves meet. So when we have two gaps, interference is going to happen because it creates two waves and they will end up meeting. So in general, when there is a gap and the waves are going to go through the gap, this is called diffraction. So the waves will diffract. Question number 5. The illustration below shows the position of Earth around the Sun at 2 different times of the year. How long does Earth take to orbit once around the Sun? This you should know. It takes the Earth a year, almost a year, to orbit around the Sun. In reality, it is 365.26 days. Okay? What is the weather in the southern hemisphere at position A? At position A, as you can see over here, the northern hemisphere, so we will divide it into two parts, which is the northern and southern hemisphere. So as you can see in this position, the axis is tilted like this. So that means the northern hemisphere is closer to the sun. Okay, so if the northern hemisphere is closer to the sun, then that leaves the southern hemisphere to be farther away from the sun. And we know that if it's closer to the sun, then it is summer. Okay, and if it's farther from the sun, then it is winter. So very simply, the southern hemisphere, it is undergoing winter. Part C. If Earth's axis of rotation is perpendicular to its orbital plane, how would the time of sunlight exposure on Earth be different? So they're saying if the axis wasn't tilted, and we know that the tilt of the Earth's axis is approximately 23.5 degrees. Okay, so if the Earth wasn't tilted 23.5 degrees, if it was perpendicular to its orbital plane, if it was like this, how would the time be different, and how would the seasons even be different? So it's gonna divide the Earth exactly into two parts. So you're gonna have, this is the Earth, you're gonna separate it into exactly two parts. And because it's separated into exactly two parts, exactly in the middle, what's gonna happen is that you're gonna have exactly two seasons. These two seasons are summer and winter. So you will not have spring and you will not have autumn or fall. Okay? And for the daylight, okay, how much will receive day and how much will receive night, you will get that exactly this half will get 12 hours day, and exactly this half will get 12 hours night. And then when the Earth finishes one rotation about itself, about its axis, you will get that this one will be on the side and it will get 12 hours of night and 12 hours of day. We know that a full day is 24 hours. So if the axis was exactly perpendicular, it would cut the Earth into two pieces, two parts, okay? And one part would get exactly 12 hours of day and exactly 12 hours of night, and the other part would also get exactly 12 hours of day and exactly 12 hours of night, and there would be only 2 seasons, which are summer and winter. So if we go to part C, we can choose the answer to be each point will have 12 hours of sunlight each day. Now, if we move on to part D, it says, what is most probably the month at position B? Is most probably the month at position B. As you can see over here in position B, the Earth, okay, so you can see that the position of the Earth at part B, it is very close to the Sun. And you should know that when the Earth is closest to the Sun, okay, then this is gonna be the month of December approximately. Okay, whereas when it is farthest away from the Sun, or not farthest, just like far away from the Sun, it's gonna be almost June, July. Okay? So keep in mind that when the Earth is closest to the Sun, it is December or even January. So December, January. But then when the Earth is farthest from the Sun, it is June or July. So if we go down, what's probably the month at position D? As you can see, we said that if it's closest to the Sun, its month is either January or December. And here the only option we have is December, so we're gonna go with December. We'll move on to question number 6. Which statements are true about water waves incident at a straight barrier? So what do they mean by water waves incident at a straight barrier? It's like you have the water waves going like this, and you have a straight barrier going like this. Okay, let's say the water waves are not there like this. We'll just assume they are like this, and this is the straight barrier. So when the water waves will arrive, they will reflect because it is a barrier. So the first thing we know is that they are gonna reflect. The second thing, okay, is that how are the water waves represented? The water waves are represented like this. They are a straight line, and you have the waves being perpendicular to the line. So water waves are represented by rays that are perpendicular to wave fronts. And one more thing, we said that it will obey the laws of reflection. That means this angle is equal to this angle. So the incident angle is equal to the reflected angle. So in this case, we have water are represented by rays that are perpendicular to the wave front. We have the angle of incidence is equal to the angle of reflection. And we have that water waves do not obey, they do obey the laws of reflection. But when a straight wave arrives to a straight barrier, it is reflected. Okay, we'll move on to question number 7. So in question number 7, they're asking, which statements describe circular waves that reach a straight barrier? So we have a straight barrier, and then we have a circular wave from this point. And then it will keep on increasing and increasing. So what's gonna happen is that it's gonna reflect. But when it reflects, it looks like what? It looks like they are bouncing back. Or in another term, it looks like what's happening is that there is a point behind the barrier that is causing the formation of these waves. So as you can see, this is what the reflection will look like. So when the circular waves will reach the straight barrier, they will undergo reflection. So of course, they're gonna obey the laws of reflection. And what happens is that it seems like a point behind the barrier is causing these reflected waves. So first of all, the circular waves undergo reflection, the laws of reflection are obeyed, and the reflected waves seem to come from a point behind the barrier. Okay, select the figure that shows diffraction of water through a narrow gap. Key term is narrow. Whenever you see narrow, that means they are going to be more curved. When it is a wide gap, you should know that they are going to be more like brackets, okay? So it's definitely this one. This case would only occur if it was like a straight line like this and a big gap, so it would occur like this. Okay, we move on to question number 9. In question number 9, they said, the diagram below shows some water waves passing through a gap between two stepping stones. So when two water waves pass through a gap between two stepping stones, this is called diffraction, first of all. And they said, what factors affect the amount of diffraction? What you should know is that there is mainly two factors that affect the diffraction. It is the width of the gap, so the smaller the gap, width of the gap, the smaller the gap, the more curved the diffraction will happen, or the more diffraction will happen, and the wavelength of the water wave. So if the wavelength is in nanometers, then the gap, of course, has to be very small in nanometers. But if the wavelength is in meters, it should not be that tiny. It should be big, like almost centimeter gap, for example. Okay, so the wavelength of the water waves and the width of the gap affect the diffraction of water. Now here, a stone is thrown into a lake after 2.6 seconds of this event. A photo of the lake surface is taken and shown in the diagram below. The dark fringes represent the peaks of the water waves. The smallest graduation of the grid represents 20 centimeters. So, the smallest graduation, meaning 1 square, it is 20 centimeters. Okay? And they told us that after 2.6 seconds, meaning from the center to the final crest, it took 2.6 seconds. Okay? They told us the water wave can be classified as, first of all, it needs a medium to move. Because it needs a medium to move, it can be classified as mechanical. If it doesn't need a medium to move, then it's electromagnetic. Okay? And because the displacement of the particles is perpendicular to the wave propagation direction, it is transverse. If it was moving along or it's parallel to the wave propagation direction, then this is longitudinal wave. Okay, now they need us to find the wavelength of one wave. To find the wavelength of one wave, okay, what we're gonna do is we're gonna take, for example, from crest to crest. Okay, you could calculate a wave like this, and then you are gonna see, okay, how much is the distance between these two waves? So you're gonna skip always this one, and you're gonna go 1, 2, 3, 4. So the distance is 4 blocks, and we know that one block, it is 80 centimeters. Was it 80 or no, it's 20 centimeters. One block is 20 centimeters. So that means 4 blocks is gonna give us 80 centimeters. Now, if you go down, they need it in meters. So to change it from centimeter to meter, you are gonna divide by 100 and you will get an answer of 0.8 meters. We'll move on to question part 2. They need the speed of the wave to 1 decimal place. To find the speed of the wave to 1 decimal place, what we're gonna do is we're gonna take the total distance traveled by these waves. So to find the total distance traveled by these waves, we're gonna start from the center all the way to the last crest. And we're gonna count how many blocks are there. We know one block, it is 20 centimeters. Let us see how many blocks there are. We have from here all the way to here. You do not count the center, so you now have 1, 2, 3. Let me do it again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we have 16 blocks. 16 blocks by doing cross multiplication, so 16 times 20 over 1, you will get that it's 320 centimeters, which is 3.2 meters. So we have it now in centimeters, it's 320 centimeters. So we changed it to meter, it's 3.2 meter. Divided by seconds, it took 2.6 seconds to travel 3.2 meter. So you're gonna divide 3.2 by 2.6 seconds, and you're gonna get an answer which is approximately 1.23. Now we move on to part 3, the frequency of the wave to 1 decimal place. Now always, to find the frequency of the wave, what we are supposed to do, or what are we supposed to do? We are supposed to take the speed and we are supposed to divide it by the wavelength, because the frequency f, it's equal to the speed or the velocity v over lambda, which is the wavelength. So frequency is equal to speed over lambda. So we're gonna take the speed, which is 1.23, and you are gonna divide it by 0.8, and you will get an answer which is 1.5375. You will round it, it's approximately 1.54, because they need to 1 decimal place. So it is 1.5, 1.54, and here it's 1.2. Anyways, if you put 1.23 or 1.54, it's gonna give you correct. But do pay attention in the exam here, they need it to one decimal place. So you would take 1.23 and round it to 1.2, and you will take 1.54 and round it to 1.5. Now we move on to question number 11. This is a very nice question. They told us the diagram below represents crests of waves spreading through the medium. The smallest graduation of the grid represents 10 centimeters. The wave propagates from S to A in 4 seconds. So they said the smallest graduation, meaning one block, it is 10 centimeters and it propagates from S to A in 4 seconds. They said the crest at A became a trough. So as you know, the diagram of a wave, it's like this. It will go from the zero to the crest, to zero to a trough, and then back to a crest again. This is what a wave looks like. Okay, this is the crest and this is the trough. So they told us they need the crest at A. When does the crest at A become a trough? We know that the distance from, or not the distance, it took from point S to point A, it took it 4 seconds. Okay? And this is the length of one wave, or it is the wavelength. And we know that we measure the wavelength by crest to crest or trough to trough. And what you should know is that the distance from crest to crest, okay, it is equal to double the distance from crest to trough. So that means the distance from crest to crest, which is wave length, it is equal to 2 times the distance from crest to trough. So I will do C to T. Okay, now that we know that the wavelength, it took it how much? It took it actually 4 seconds. So the wavelength, we know that it's double the distance from the crest to the trough. If it took from crest to crest 4 seconds, then for sure it's gonna take from crest to trough 2 seconds. All right, so over here it's gonna be 2 seconds. Now, as the crest at A becomes a trough and then a crest again, the wave propagates by another blank centimeter. So they said, again, let us draw. We have a wave like this. It's crest, trough, crest. They said, as the crest at A, so this is the crest at A, it becomes a trough. And then it becomes a crest again. So it's doing what? It's moving one full wavelength. They want to know how much is the distance. So how much is the distance of one wavelength? All you need to do is draw and it will be easy. So from crest to trough to crest, or if you ignore trough, it's going to be from crest to crest, which is the value of wavelength. How much is one wavelength? Very simply, to find the value of a wavelength, what we are going to do is we are going to come from here and we're going to count it until here. So how many blocks are there? We have 1, 2, 3, 4, 5, and 6 blocks. Okay, and they told us the smallest graduation is 10 centimeters. So one block is 10 centimeters, so times 10, you will get 60 centimeters. So the total distance, it is 60 centimeters. Now we move on to question number 12. In order to locate their prey, a bat sends out sound waves. When the sound waves hit an object, they bounce off the object and return to the bat's ear. A bat listens to the echo produced and figures out where the insect is and how big it is. A bat can emit sound from 12 kHz to 160 kHz, given that the speed of sound in air is 340 meters per second. Now, the sound with the longest wavelength that a bat can produce. Okay, first thing we need to know is that wavelength, lambda, it's equal to the speed v over frequency. Okay, how did we get it? If you remember the equation, frequency times lambda is equal to velocity. You have the speed of sound in air, which is 340 meter per second. And then they need what? They need the longest wavelength. So to take the longest wavelength, you need to take the smallest frequency. So over 12 kilohertz. Okay, you're gonna put it on your calculator, 340 over 12 kilohertz. We will not change it to hertz, because if we change it to hertz, we're gonna get our answer in meters, but we need our answer in millimeters. So to make our answer in millimeter, we can directly divide by kilohertz. So it's gonna be 340 divided by 12 kilohertz. You're gonna get an answer which is 28.333. You can put it like that, or you can put it to the nearest integer as 28 millimeters. So over here it is 28 millimeters. We'll move on to B. Okay, the bat hears the echo 0.05 seconds after it screeches. So it will send the sound to the insect, and the insect will, the sound will bounce back from the insect to the bat. So in reality, how long does it take the sound wave to fly to the insect or to move to the insect? It takes 0.050 divided by 2, which is 0.025 seconds. Okay, so now they want what? They want the sound to 1 decimal. I think they want the distance, okay, that the sound wave bounces off of. So what you should know, that distance, it is equal to what? It is equal to the velocity times the time. So you're gonna take the velocity or the speed, which is 340 meters per second, and you're gonna multiply it by 0.025 second, and you will get an answer of 8.5 meters away. Now we move on to question number 13. Here, an electromagnetic wave has a wavelength of 120 nanometer in vacuum. What part of the electromagnetic spectrum does it belong to? Here you should memorize the electromagnetic spectrum. It's this one over here. I want to find a more accurate one, because this one is not really that accurate, because in the book it will say something different. Okay, so this one over here, I found it to be one of the most accurate ones. So what you need to know is that the length of a radio wave, it is in between 10,000 meters, because this is in meters, so 10,000 meters and 0.1 meter. So look, the radio wave, it is between 10,000 meters and 0.1 meters. The microwave is between 0.1 meters and 10 to the power of minus 5 meters. Infrared is between 10 to the power of minus 5 and 5 times 10 to the power of minus 6. And then 5 times 10 to the power of minus 6 visible is in between this and 10 to the power of minus 8. Ultraviolet is in between this, and X-ray is in between this and this. So what we are looking for, if you go back, you will see over here that the electromagnetic wave has a length of 120 nanometers. 120 nanometers, it is what? It is 120 times 10 to the power of minus 9. But always, as you saw before, they're taking it to 2 significant figures. So if you took it to 2 significant figures, it would be 12 times 12.0 times 10 to the power of minus 8. So you will go back to the electromagnetic spectrum and you will see which one is to the power of minus 8. It is ultraviolet. So definitely the answer is going to be ultraviolet radiation. Now for part B, they said choose the correct answer to complete the sentence. The frequency of the electromagnetic wave is, very simply, what you need to know is that the frequency, it's equal to the speed of light in vacuum over lambda. Again, it's like times speed of light, you can put it as velocity. Okay, speed of light, C, you should remember it's 3 times 10 to the power of 8. Okay, so what we're gonna do is on the calculator, we will put 3 times 10 to the power of 8 divided by 120 times 10 to the power of minus 9, because it is nanometer. Put it on the calculator, you get 2.5 times 10 to the power of 15. So this is our answer. Let's submit, and hopefully we do not have any mistakes. Thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.